The last rule that we're going to need for this unit is called the inverse rule for derivatives. So we're going to learn how to take the derivative of the inverse of a function without actually having to find that inverse function. So before we start that, let's think about a few things that we know about functions that are inverses of each other. So a lot of this is just kind of good knowledge that we should have, generally speaking, but we know that if two functions, f of x and g of x, are inverses of each other, we know they're reflections over the line y equals x of each other. So that's one thing we know. We know that we would exchange the domains and the ranges of these functions. So the domain of f is the range of g and vice versa. We should know how to find inverse functions, right? Normally we would replace the x with y and vice versa and solve. We want to actually find the inverse function. And another important thing that we know about inverse functions is that if we have the composition of f of g of x, they will always end up equaling x if the functions are inverses of each other. And likewise, g of f of x will also equal x. And so it's this fact right here that we're going to actually use to develop the rule for finding the derivative of an inverse function. So we're going to just start with f of g of x is equal to x. And we'll make a note off to the side that this is true if f and g are inverses. And so if f and g are inverses, f of g of x must equal x. And we could then take the derivative with respect to x on both sides of this equation and still be left with a true statement. So we know how to take the derivative of f of g of x from the chain rule. That the derivative of f of g of x is f prime of g of x times the derivative of g prime of x. And we know that the derivative of x is just 1. Well, we're actually pretty much done here now with finding our rule. What we're going to do is we're just going to divide by g prime of x. So we're going to have f prime of g of x is equal to 1 over g prime of x. And what we'll do is then note that for g, we know that at any x value, the y value is g of x on g, which means that g must contain that point. Another thing that we know about inverse functions is that you can always exchange the x and the y values to find a point on the other function. So we know that there's some point g of x, comma x on f. So all we're going to do to come up with a rule that kind of makes a little more sense than this one is we're just going to let a equal x and b equal g of x, right? Where a and b are just some values, some constants, which would indicate to us that g must contain the point a comma b, where f contains the point b comma a. And so I'll just go in then and replace g of x in this formula with b, because we said g of x is going to be called b. And so I'll just end up with f prime of g of x, or f prime of b, is equal to 1 over g prime of x. Well, g prime of x is the same as g prime of a, because we said that a is equal to x. And as long as f and g are inverses, and g contains the point a comma b, or f contains the point b comma a, we can always find the derivative of the inverse function. Let's say f. We can find the derivative of f at at b by just taking 1 over the derivative of g at a. Right? we'll just exchange those values, A and B, from F to G. And that's our inverse rule. That's really all there is to it. Right? Here it is again, and this time I think I've written it just the opposite way, where we've got f prime of A and 1 over g prime of B, right? F of x contains A, B, and g contains B, comma, A. And so this is the inverse rule, and it'll allow us to find the derivative of the inverse of a function without actually finding the inverse function. So let's take a look here at f of x equals x cubed, where g of x is the inverse of f. And we're going to see if we can find g prime of 8. So obviously we could find the inverse of f of x. We could find g of x and then evaluate that derivative at 8. And we'll do that at the end just to check our work here. But let's try to use the rule. We know that g, if we're looking for g prime of 8, we know that g must contain a point 8, comma, something. If g contains a point 8, comma, something, then f must contain a point something, comma, 8. That's one of our rules for inverse functions. So I can use our function for f of x, which is equal to x cubed, must equal 8 somewhere. Well, that'd be when x is equal to 2, right? So I can take that 2 and put it in here. And now I've got the set of points. And if I'm looking for g prime of 8, g prime of 8, according to the inverse rule for derivatives, ought to be 1 over f prime at 2. Right? We just use the opposite value from that point. So g prime of 8 is 1 over f prime of 2. Well, find f prime of x really easily by taking the derivative with the power rule. F prime is 3x squared, and f prime of 2 is just, well, looks like that's 3 times 2 squared, or 3 times 4, 12. So g prime of 8 is 1/12. And we did it without actually finding the inverse function. Now, if we really wanted to, we could go about finding that inverse function just to make sure this is right. We know that y is equal to x cubed is our f of x function. So we would exchange the x and the y values to give ourselves x is equal to y cubed. And we'd resolve this for y, where y is the cube root of x, or our inverse of f inverse of x, which is also equal to g of x. So g of x is cube root of x, or x to the 1/3. G prime of x ought to be 1/3 x to the negative 2/3. And if we're looking for g prime of 8, this would be 1 over 3. Then we'll drop that x to the negative 2/3 into the denominator. It's an 8 to the positive 2/3. And we end up with 1 over 3 times 8 to the 2/3. And we can easily evaluate 8 to the 2/3. Just do the cube root part first and get the cube root of 8 is 2. Then square it to get 4. And we can see that we end up with the exact same value, 1/12, that we got using the inverse rule. So it's really up to you which way you want to do these. But it's pretty common on the AP test for them to give you a problem where it's not going to be easy or even possible for you to find the inverse function. So we'll look at one of these right now, and then this was going to really be it for this unit. We're given f of x equals e to the x plus x. And we know that g of x is the inverse function of f. And I want g prime of 1. Well, g prime of 1 means that g contains a point 1, comma, something, which means that f contains a point something, comma, 1. So we'll just set f of x equal to 1, because the y value here that we're looking for f is 1. And we'll see if we can come up with the value. Now, this isn't a real easy equation to solve. But if you think about just a couple of pretty straightforward numbers that you could plug into there, I think we'd see that if we tried 0, well, e to the 0 is 1, and 1 plus 0 is 1. So it looks like that works out real nicely. And we have G contains a point 1, 0, where F contains a point 0, 1. So if we want G prime of 1, G prime of 1 ought to equal 1 over F prime of its x value, 0. So then we just need to find F prime of x, and the derivative of e to the x is e to the x, and the derivative of x is 1. So when we evaluate F prime of 0, we get e to the 0 plus 1. E to the 0 is 1, so we end up with 2. So we now know that F prime of 0 is 2, which tells us that G prime of 1, or 1 over F prime of 0, is just 1 over 2. And we're able to do that with a function that it's not really going to be possible for us to find the inverse function of it very easily at all. And that is how the inverse rule for derivatives works. That is the end of our unit on derivatives.